Hi guys, today we are going to have a little look at actually calculating the energy change that happens when a chemical reaction does. First though, I would like you to have a go at answering the questions that you can see in front of you. Hopefully it won't take you very long. I'm just going to pause here for a second so that you can do those. Okay, so hopefully you have managed to do those. Hopefully you got that the answer to question 1 was, well, we had hydrogen and oxygen creating water. That was our word equation. We then had that when a reaction takes place, energy is supplied to break the existing bonds and energy is released when new bonds are formed. You hopefully got that which energy change A, B or C represents the activation energy. Hopefully you got it as being B. It's always from the reactants to the top of the hump. And then which energy change shows the reaction is exothermic. That would be A, the fact that that energy has gone down. Arrow C is actually nothing. Explain why the hydrogen and oxygen needed a spark or flame to start the reaction. Well, we need to provide enough energy for the reaction to start to break the bonds, basically. Okay. So today we are having a look at the energy change of reaction. This is higher tier only, and I'm going to show you a way of formatting these answers, and I've chosen this because it is the easiest way, I think. Ultimately, it's maths. You can lay it out in a variety of different ways, but generally the maths that you do in chemistry isn't actually all that complicated. What is complicated is making sure that you're knowing what you're doing. So the layout that I'm going to give you is there for that. Okay, so here we have an example of methane over here reacting with oxygen to make carbon dioxide and water. Now I've drawn this out in its entirety and I'm asking what do the lines represent. Hopefully you've had an idea. The answer is that they are representing the covalent bonds that are going on. Hopefully you remember that a covalent bond is a shared pair of electrons. Okay. What happens to these chemicals for the chemical reaction to happen? Well, first we have to have the bonds over here breaking, and then we have to form these bonds. Okay, so different reactions give out or absorb different amounts of energy. How can we work out how much? Well, we can use the amount of energy necessary to break the bonds and the amount of energy released when the bonds are then made. Okay, so does bond breaking absorb energy or release it? Bond breaking absorbs it. We're having to put energy in to pull them apart from each other. As a really bad analogy, because it's not magnets, imagine you had a pair of magnets. Yeah, some of those strong little neodymium magnets. If they're stuck together, you have to put in force, energy, to move them away from each other. If you then hold them near to each other later, they're going to want to attract towards each other and release energy when they snap back. That's why you hear it go click. Okay, so breaking bonds absorbs energy, making bonds releases it. I came up with a really terrible idea of it's if you've had a really weird day and suddenly someone decides to break into your house and make out with you. Very odd day, but its energy is going in when they're breaking, hence breaking in, and then energy is coming out when they're making out. And you'd probably be a bit livid if that happened. So, what we need to do is, if we were given an equation like this, I would always recommend drawing out in full. Okay, remember that each of these lines is representing a single covalent bond, so we've got double bonds between all of these oxygen molecules. Okay, so we've got methane here, oxygen, carbon dioxide, water. You will notice that underneath this, I have got the bonds that are going to be broken on the left-hand side, the bonds that are going to be formed on the right-hand side, because conveniently the energy change is the energy that is being absorbed, energy going in, so that's going to be a positive value, take away the energy that is released. When you come to a question like this, they will give you that information. I'm not expecting you to try and memorise what all of the bond energies are for a whole load of different substances. You will just be told that. Okay, I haven't got it on here, but let me go through and then I've got an example for you. So, first off, I will list all of the bonds that are being broken. So we've got 4 carbon-hydrogen bonds, 1, 2, 3, 4, and we've got 2 oxygen-oxygen double bonds. I'm not allowed to move that. Okay, so these are a double bond, so it's important that we note that. Okay, here we have 2 carbon-oxygen double bonds, and then we have 1, 2, 3, 4. We have 1, 2, 3, 4 oxygen-hydrogen bonds. Okay, so these are the bonds that are being broken, energy is going in. These are the bonds that are being formed, energy coming out. So we would look up, and we would have found that the bond energy for a carbon-hydrogen bond is 413. So we're going to do 4 lots of that 413. If I'm being really picky, this is in kilojoules per mole. I've not written it here. Fundamentally, it doesn't really matter for this because they'll always give you it in kilojoules per mole. Okay, we've got 2 oxygen double bonds. Each of those double bonds has an energy of 498, and we've got 2 of them. So we have those. That is all of the energy that we're having to put in to break those molecules apart. All we do is we just add that all together, and we get a value of 2,648 kilojoules per mole being put in. We just do the same on the energy that is being released. So we would look up and we would find that carbon-oxygen bonds are pretty strong, and we got 2 of them, so we do 2 lots of 805, and we do the same for the hydrogen-oxygen bond, if I'm allowed to move it. There we go. And they're not as strong. We've got 4 of them, and then we just add that together, and we've now got the total amount of energy in over here with 2,648, and we've got the total amount of energy out, 3,466. To work out the energy change of this reaction, we do the energy absorbed to take away the energy released. For some reason I don't have that. So we would have 2,048, take away 3,466, and that will give us a value, and those of you that are very good at maths, hopefully, will have noticed that this is going to be a negative value, which it will be. So 2,648 take away 3,466, which should give us a value of minus 818 kilojoules per mole. Sorry, kJ. We'll do it like that. Okay, that's it. That ultimately is it. The math itself is not terribly hard. You just need to make sure that you're counting up the right number of bonds. One of the things that they can do is they might draw a part of it out for you, but have indicated that you've got 2 of it. It's always worth drawing it out again. Okay, so we need to use that to redefine our exothermic and endothermic reactions. So we hopefully had thought about exothermic reactions as being reactions that give out heat energy, exiting, and endothermic reactions as being reactions where energy is entering the chemicals. Okay, we need to be able to couch that in terms of the bonds being broken and the bonds being made. So an exothermic reaction is a reaction where more energy is released in bond making than is absorbed in bond breaking. Okay, that's going to mean that it has a negative energy change. That might seem weird, but that's because we're talking about the energy of the chemicals themselves, not the energy that has been given out. Okay, our endothermic reaction. Right, let's just delete this instead of trying to move it. An endothermic reaction is where more energy has been absorbed in breaking bonds than is released in making the bonds. So it's going to have a positive energy change. If you remember, that's why we have the hump that goes up, because energy has been put in, and for our exothermic reaction we have the hump that goes down, because energy has been released. Okay. So if we did another example, so we've got hydrogen reacting with oxygen to make water. You'll notice that I've indicated that there are generally 3 marks for this. Often they actually are not necessarily too bothered about whether you get the right positive or negative, because they'll just ask for the energy change. So they're looking for the magnitude rather whether you've got it the right way around. But if you do it this way, the way that I formatted it, you should get it exactly right each and every single time. Okay. So this time you'll notice that I have actually given you a little table with the bond energies. You'll notice that that says it's kilojoules per mole. What I would like you to do is I'm going to give you the opportunity to pause now, see if you can work it out, and then we'll see whether you got the right answer. So I'm just going to stop for a moment. Okay, so hopefully you had that on the left hand side we had 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen double bond. That is 2 times 436, which is 872. You hopefully also got that that was 1 lot of 498. That is 498. So our total is 872 plus 498, giving us 1,370. On the right hand side, hopefully you correctly identify that we've got 4 hydrogen-oxygen bonds. And our hydrogen-oxygen bonds are 464. So we're going to do 4 times 464, which is 1,856. So we've got a mark for having the right amount of energy absorbed, a mark for having the right amount of energy released, and then we're going to do our calculation. So let's take away right. So we've got 1,370 take away 1,856, and that gives us our final answer of minus 486 kilojoules per mole. A double check for that for us is that that is a negative value. That is good because it's an exothermic reaction. Burning something, they're always exothermic, so the fact that it's a negative value is good for us. It's a good little just double check. Okay. On the worksheets that I've added along, I've also got this question, which I will show you worked out on a piece of paper in just a second, just in case you are still a little bit stuck. And then I've got the answers for them on the next couple of slides. So please, if you're still a little bit stuck, have a watch of me working out this question on the paper in a moment. If you have got it all absolutely fine, then keep cracking on, do the questions on the worksheet, come back and have a look at the answers at the end of this. Okay, so I'm just going to switch and we're going to have a little look at what I would do for this in its entirety. Okay? Okay, so this question is actually one that we've already done, but with very slightly different numbers. So the first thing to notice is that in the way that they have drawn this, I saw a number of people last year make this mistake. So with the way that they've written that out, I did see a number of people get the number of bonds over here wrong. Remember that this indicates that we've got 2 of the whole thing, so we could just redraw them out, but ultimately it doesn't matter. So we've now got that. I'll split it in half. We have 4 of the C to H bonds over here, so 1, 2, 3, 4. We've got 2 of the oxygen-oxygen double bonds, like the same. Over here we've got 2 of the carbon-oxygen double bonds, and we have 4 of the hydrogen-oxygen bonds. The reason we've got 4 is that each molecule has 2, and we've got 2 molecules, so we've got 4 in total. So that gives us 4 times 414 in this case. The numbers are very slightly different, so that's 1,656. We have then 2 times 498, which is 996. And this symbol I'll use just is sum, so adding those together is 2652. On the bonds being formed side, we have 2 lots of 803, which is 1,606, and we have 4 lots of 464, which is 1856. If we just add those together, we get 3462, and then our energy change is 2652 take away 3462, which which is minus 810 kilojoules per mole. Okay, hopefully that made sense. It is effectively what we've done before, but that is how I go about laying these out. I always recommend to draw what your molecule is. So, for example, say that they had said that it was butane. Yeah, I would then go, okay, I remember butane. Bute is 4, so 1, 2, 3, 4. And it's an alkane, so all of these bonds are single bonds. And we've got hydrogens off all of those. With the information you had in that question, you could actually work out the energy change of the reaction of butane reacting with oxygen. You just need to work out the balanced symbol equation first. But they'll rarely require you to work out the whole thing. But it's quite common for them to have given sort of a little sneaky thing of where it's multiple molecules or something. Okay, so question 1's answers for part A, minus 810. Showed you the breakdown for that. Part 2, because energy is needed to break the bonds, and that is less than the energy release when bonds are formed, so go back to that definition previously. And then to provide the activation energy or to break bonds. Okay, question 2. We had, well, there we go, those are the marks. So the first, the bond's broken, the total energy is 2,148. Bonds made, 2,354. First number take away second number gives us minus 206. Notice that here again they've said don't worry about the sign. Okay, and again looking back at our definitions before. Question 3, a lot more. Remember that this delta H means energy, well, enthalpy change, heat energy change. So that's our activation energy. So here we go, again we get a mark for the bonds broken, a mark for the bonds made, and a mark for our answer overall. And here. If you ever get a question where they ask you this and then ask you how that demonstrates that the reaction is exo or endothermic, make sure you quote either something about the overall energy change and specify that number, make sure you get the sign right, or talk about how much energy is being used to break the bonds, or absorbed to break the bonds, and how much energy is being released when the bonds are being made. Okay, last question. So as usual, 1 mark for the total energy for the bonds being broken, 1 mark for the bonds being made, broken, takeaway made. And again, they're not bothered about the sign here, but in subsequent questions sometimes they are. Now don't forget that it's never just about the bonds that we're forming or breaking are stronger than the other, because that suggests that each bond is stronger. It's to do with the strength of the bonds and how many of that particular type of bond you've got. So we're just talking about the energy from the bonds being broken and the bonds being formed, rather than specifying that the bonds are stronger or weaker. Okay, energy barrier needs to be overcome, or we need to give the activation energy, and catalyst lowers the activation energy. Okay, hopefully that's all gone alright. If you could please let me know how you got in with these questions, and let me know of any questions that you've got additionally. I hope that you found this helpful. Thanks. Bye.